some remarks on Landau Siegel zeros, and start with connection with class numbers. So Dirichlet, first of all, introduced his Dirichlet characters 1837. And he proved that there are infinitely many primes in any given arithmetic progression of this form. P is congruent to A mod D and AD relatively prime. And one of the key steps in the proof was to show that L1 chi is not zero for any non-principal character. He needed this. So he was able then to take a linear combination of these functions or the logs, for instance, and he doesn't want the log to be infinite. And he developed his class number formula, for instance, this that we see. If we have an imaginary quadratic number field and h of minus d is the class number, and then we have this connection with L1 chi d. So in this way, we know that since the class number is positive, is at least one, it's the number of elements of a finite group, then L1 chi d is larger than or equal to pi over square root d. So constant over square root d. And it might be surprising to know that at least as far as effective results are concerned, we don't have much better bounds. I mean, just a log better, if you call this. Okay, so connection with class number, we have this lower bound, and in what follows, I just write chi for this character mod d. So Dirichlet character mod d. But for some applications, the lower bound, this lower bound, it's not strong enough. Assuming the generalized Riemann hypothesis, then one knows that L1 chi d is between, say, 1 over log d and log d. Some absolute constants here. But unconditionally, it's much easier to get an upper bound. And we have an upper bound of this form. L1 chi d is less than, so less than or equal to a constant, an absolute constant times log d. But lower bounds are much more difficult to obtain. And the main reason, or in some sense it's an equivalent reason, is that we cannot rule out, we don't know how to rule out a possibility of existence of a real zero, say beta of L1 of LS chi with beta close to S equals 1. And such a real zero was called the Siegel zero, and now, I mean, starting 20 years ago, or when we call it the Landau Siegel zero. The classical zero-free region for Dirichlet functions show, or are of this form, that there are no zeros in regions of this form when we compute L. So L is a Dirichlet function, L of sigma plus IT chi at a point sigma plus IT where sigma is larger than or equal to 1 minus a constant, and again, absolute constant here, over log of something like qt, or let's say t plus 2 here. So we have this zero-free region with exceptions, and the exceptions are the so-called Landau Siegel zeros. If we have, and then chi is called an exceptional character if it has a zero in the region. Now, if that happens, that chi is a real character, and the zero is real, so a zero that looks like this, it's beta. L of beta chi is 0, with beta larger than 1 minus this constant over log q. And in that case, this particular Dirichlet function has a single Landau Siegel zero. But if we take the totality of all the Dirichlet functions, we may have even many Landau Siegel zeros. They do tend to, we know that they do repel each other. So if you have, if we have say a Landau Siegel zero for a character mod Q, then, and a bad one, let's say where beta it's closer than, say, it's a distance smaller than 1 over log Q, maybe 1 over log square or 1 over the Q to the epsilon or things like this, then we have a much stronger repulsion. And these zeros will also repel other zeros of other Dirigel functions or other zeros in general, let's say. Now, Landau showed that exceptional characters, if they exist, appear only rarely. That's what we're talking about. And Hecke showed that there are no real zero in the classical zero-free region. If there are no real zeros, then L1 chi is larger than 1 over log D. So this is a strong statement. Then in this case, the class number, we have this inequality for the class number. It's larger than a constant times square root D over log D, which is incredibly strong compared to what we know unconditional. Or if we put this result, if we rewrite it in a different way, if L1 chi is, let's say, much smaller than 1 over log D, let's say like little o of 1 over log D, then LS chi has a Landau Siegel 0. And now we talk about what Professor Sarnak mentioned before we started to record.
And my name is Peter at this point. Come on.
Okay. So what Peter said before is that this is what Landau proved. And this is what Siegel then proved. And we noticed that they both proved this in these results. Both of them are ineffective. So Landau obviously had the right idea, and then Siegel, so to speak, pushed it to the limit. And he got that L1 chi is larger than a constant depending on epsilon over D to the epsilon, or any fixed epsilon. And the constant is ineffective. In fact, as I mentioned, I guess before we started to record this talk, that Peter sent me, when we wrote a paper on this, that I'll mention briefly the paper later on, he sent me to the library to look at the two papers and see that indeed Landau had the main ideas. He uses auxiliary functions to, and so on. He had the main ideas. And it's interesting that not only that there are papers that appear in the same year, but on the same journal. In fact, it's Acta Arithmetica, and it's the first volume of Acta Arithmetica. Landau published it there, and Siegel immediately find out, and then immediately did it and immediately published it. Okay. None of these is able by themselves to solve the so-called Gauss class number problem. For this, we need an effective lower bound, and this is provided by work, say, by Goldfeld, and in combination with work from Gross and Zagier. So the combination of their work is that h of minus d is larger than a constant times log d and the product over times divided. And this allows, in principle, to solve the class. First of all, it solves the class number 1 problem that was solved earlier, but it solves the class number problem in general. If you fix an h, like h is 5 or 7 or 10, this allows us, in principle, to find all the imaginary quadratic fields with class number, that given number h. Some results that kind of use knowledge of Landau Siegel zeros. Knowledge in the sense that you can do something if you don't assume the existence of Landau Siegel zeros, or if you assume that Landau Siegel zeros do not exist, and you can do something else. And sometimes the result is better, maybe surprisingly, but sometimes the results are better if you do assume the existence of a Landau Siegel zero or a sequence of Landau Siegel zeros. Linux theorem is well known. It says that there exists an absolute constant, L, such that in any arithmetic progression, there is a prime P congruent to A mod D. If this is the arithmetic progression, A, D relatively prime with P less than D to the L. And I think the current record is L equals 5, if I remember correctly, from 2011, Xiloris. But assuming a strong lambda, or assuming there is a strong lambda equals 0, or in other words, that L1 chi is very small, for a convenient chi, depending on this, then Friedlander and Ivanets in 2003 have shown in certain ranges that you can push this L to some constant that's strictly smaller than 2. And the whole point here is that what's known under GRH is that you can take L to be like 2 or 2 plus epsilon. So of course, what we expect to be true is that this holds for L 1 plus epsilon already. Like in arithmetic progression, mod D, if you look at numbers in a given arithmetic progression less than D to the 1 plus epsilon, they should be prime numbers. But what is known, as I said, we need something like D to the 5 unconditionally, but assuming GRH is known, I'm not saying that this is what you can do. So when I say that the result goes beyond GRH, I mean only that, because I don't know what other people are able to do. If you allow them to use GRH assumption, maybe they can do much better than us. But I mean, what is known? It's known that you can make this L less than 2 plus epsilon. And then in some ranges, if you assume the existence of lambda equals 0, they can push this below 2. So this is an example of a result where you can do better than expected by using this assumption. And people call this illusory results because in fact there shouldn't be any lambda equals 0. If we believe GRH, as I do for instance, then we don't think that there should be any lambda equals 0, but they cannot exist under GRH. So some of these results look impressive, but they would lose content if someone proves that there are no lambda equals 0s, if they are eliminated. But why prove such results like Friedlander Ivanets? I don't know if any of them is present today. We can ask them directly, but if not, let me give an answer. Some results require considering separately the case where a lambda equals 0 exists and the case when it does not. So then it's useful to make this distinction. And let's say more philosophically, such results test the strength of the hypothesis that lambda equals 0 exists. And also give a way to measure the strength of present tools and power of current technology. Now, some such results. Well, first of all, if we assume the existence of a lambda equals 0, or if we assume the existence of an infinite sequence of lambda equals 0s. Because if you assume the existence of one lambda equals 0, then it will have influence in a certain range. But if we assume infinitely many, then we can combine them and get some better results. For instance, the first one, half the arithmetic progressions contain about twice as many primes as expected. And then the other half will contain very much fewer primes than expected in a certain range. Of course, we know the prime number theorem in arithmetic progression. When you look at primes in a much larger range than the modulus, then the effect of the lambda equals 0 starts to disappear, and then we do have the correct asymptotic form. Another type of result like this by Hillbrown in 1983. There are many twin primes or pairs of primes at a distance, a fixed distance h. Of course, he wants to get a result like this. There are infinitely many primes. It's not enough to assume the existence of a single lambda equals 0. So he will, if you look at his paper, he's assuming, as I said before, the existence of infinitely many lambda equals 0s. if there is a sequence like this, or there is no sequence, in which case you say there are no Landau Siegel zeros because there is no sequence of Landau Siegel zeros. Okay, another type of result, Friedlander-Ivanez in 2004. If you assume the existence of a good enough or strong enough Landau Siegel zero, then they can show that in a certain range, you can find prime numbers in intervals that are short. Short meaning shorter than square root type, like intervals of the form x and x plus y or x minus y with y less than square root x. We know that the Riemann hypothesis, I'm not talking about generalized Riemann hypothesis, just Riemann hypothesis for the Riemann zeta function allows one to show that there are prime numbers in any intervals of this form. X plus square root x, or square root x times the power of log. And one more result, 2005, again, Friedlander-Ivanez. There are infinitely many, again, if we assume a sequence of Landau Siegel zeros, then there will be infinitely many primes of this form, a power of 6 plus a square. And they also have a nice application because they can change this slightly, so they can make it like this, infinitely many primes of this form for this discriminant form, which means you can interpret this as saying that there are infinitely many elliptic curves with only one place of bed reduction. But again, this is not unconditional. None of these results are unconditional. All of them use the assumption of existence of Landau Siegel zeros. One more result. Again, Friedlander-Ivanez, 2013. They show that if chi mod D is exceptional, meaning again, L1 chi is very small, then D is the sum of a prime and a square, which is a nice result, taking into account the conjecture, well-known conjecture of Hardy and Littlewood in 1923, that every large number is a sum, every large non-square.
I have a question. So,
oh yes,
what exactly do these things about being the sum of a prime and a square have to do with Siegel zeros? You haven't explained the relevance yet.
Yeah. Well, if we have a, let me just give a naive explanation, but this is
just like under GRH. Can you already were these things known in earlier dates? Like, was this?
I don't think that. What? No. On GRH, you don't have.
Doesn't
it.
help you.
Okay,
No,
so then why are Siegel zeros relevant then?
Okay, Siegel zeros are relevant. For instance, if we think about this imaginary quadratic field, Q of square root of negative D, there will be, if L1 chi is very small, but if there is a Landau Siegel zero, then what happens is that there will be lots and lots of primes for which chi of D, or which chi of P, it's -1. And primes are of two types. Some of them are inert, some of them split. So when they split, if a prime splits, let's say, then P, let's say, if we assume that the Landau Siegel zero is so bad, if the Landau Siegel zero is so bad that the class number is 1, let's just to simplify the discussion. Let's say the Landau Siegel is so bad that L1 chi is like 1 over square root DD, then the class number is very small, like 1. So then this, in that case, in this extreme case, all ideals will be principal. So we know that any prime that splits will then split as a product of two principal ideals that will look like x plus square root of minus x plus y square root of minus d times x minus y square root of minus d. So this means x squared plus d times y squared. So this quadratic form, x squared plus dy squared, has lots and lots of primes in it. In fact, I think there is There is an if and only if criterion for class number 1 by Rabinovich from 1940s, 1950s, which show that the class number is 1 if and only if all these numbers are prime. Something like x squared plus d or x squared plus dy squared up to a certain bound have to be prime numbers. Yeah, that would be the connection.
I'd answer him very cleanly. Of course, if these theorems were known under Riemann and against Riemann, then you would have it unconditionally, like you'd prove twin primes.
Okay, very quickly. Well, I'm afraid that there are so many results that are so nice that I won't have any time to talk about recent result of mine with a couple of co-authors, but I will just briefly state the result at least. So, but let me say a few more things. Landau Siegel zeros, for instance, distort the pair correlation function for the zeros of the Riemann zeta function. People call it Montgomery pair correlation. And that was known to Montgomery, was known to Heath-Brown, and more recently, let's say in 2002, I think there's a paper of Coney and Ivanez that showed that if you have a Landau Siegel zero there, then almost always in a certain range, the distance between zeros of zeta is at least half of the average. So if you can find zeros of the Riemann zeta function, now has nothing to do with this Dirichlet function, that the distance is significantly smaller than the average, like 1/3 the average or things like this, and if we find lots of them, that would disprove the existence of Landau Siegel zeros. Let me also briefly mention this result. Peter and myself from 2000 or 2001. This is done under a certain hypothesis that we call hypothesis H, which is that we allow L function in general, or in particular Dirichlet functions, to not satisfy GRH, but only to not satisfy them because they have real zeros. So in other words, we assume hypothesis H, meaning that we assume the GRH holds for all Dirichlet functions, except for possible real zeros of any of number of such functions. Now, this is still interesting because if we say except other type of zero, then by definition we don't allow Landau Siegel zeros, but we do allow them to exist by this assumption, because we allow them to have any number of real zeros that we want, but not any other type of zero, not complex zeros. And in this case, we show that there are no sequences of Landau Siegel zeros. In fact, we show something much stronger than that. In particular, we show that L1 chi is larger than a constant depending on epsilon, not only over d to the epsilon or c of epsilon over log q, but we can show that L1 chi is larger than c of epsilon over log q to the epsilon. I don't know if I made myself clear here, but let me do something just to show some expertise with this Zoom type work that now we use in class. What I was going to say is under that hypothesis, then we show that L1 and let's say chi d, it's larger than or equal to a constant depending on epsilon. So in other words, for any epsilon larger than 0, the statement starts like this. For any epsilon larger than 0, there exists a c sub epsilon. This is still ineffective because we follow the same type of proof. But instead of d to the epsilon, as in Siegel's theorem, we take a log here. Surprising. So it's much stronger than this. Log d to the epsilon. In particular, we can take epsilon to be 1, and then we have a constant, absolute constant there, but ineffective over log d. That was just the boundary of, in this terminology, the Landau Siegel zeros compared to other type of zeros. So these are much weaker lambda equals zeros, and we can still show that they don't exist under this assumption, very strong assumption of GRH, except for those type of zeros. So let me share the screen again. Continue with that. Very quickly, one can ask about the mechanism underlying such results. As I mentioned, if you even think about just the L1 chi as a product, like an infinite product, or just to approximate it by a finite product. Now, if we want this L1 chi to be small, then what I said earlier, then lots of p's are such that chi of p is -1. Because you see what happens when chi of p is 1, then 1 minus 1 over p is smaller than 1. Yeah, but you have this to the -1. So this factor is larger than 1. So anytime I have a chi of p that's 1, it increases the value. So it must have many more primes p for which chi of p is -1. And say more rigorously, say we can prove this. It's not difficult to show. And this is unconditional. That if you look at Dirichlet convolution of 1 and chi, 1 the constant function, constant arithmetic function 1. If we think about what this means, that corresponds to a product of Dirichlet functions, one of them being the Riemann zeta function and the other being our function. That's supposed to have a lambda equals 0. I'm saying I'm not using at this moment to prove this. I don't need to know that this has a lambda equals 0. That's what I'm saying. This is unconditional result. And you take the sum up to a number x. Say x is larger than the modulus d, large enough so that this error term is smaller than 1. For instance, if x is larger than d, that's good enough. But I can take x to be larger than like square root d, then x to 1 over 2 is larger than the 4th root of d, and this makes it small. But if you take x to be larger than d to the 10, then this is negligible. Okay, which is what we'll do later. And so this sum is equal to L1 chi times log of x plus, this gamma is Euler's constant, plus the derivative of our Dirichlet function at 1. Now, normally, or under GRH, for instance, under GRH, and just to see the difference, the big difference between the two scenarios. Under GRH, L1 chi is larger than 1 over log d. So if I take x to be like a d, I get a log d over log. So this goes to infinity as d increases. But if instead I take a Landau Siegel, I take a chi and I assume that there is a Landau Siegel 0, and we take x like a d. But even if I take x to be d to 100, log of this is just like 100 log d. So I take x to be huge, like d to 100. This is still 100 log d. And this is smaller than 1 over log d by our assumption that there is a Landau Siegel 0. In that case, this is an asymptotic formula, not for L1 chi, but for the derivative. And we can play with this a bit more. And if we subtract one such sum from another, as I said, if we subtract this, the sum up to d squared, say, from the sum up to d to a, where a is a much larger number, a fixed number, then we get that the sum is less than L1 chi times log of d to dA. Now, in a couple of results that I'll mention a bit later, we will work with values of the size of d to 300 or something like that. What I'm saying, in a range like this, d to 300 is like log of this is just 100 log d. So if our log is less than 1 over log square, this is small. Now, if I have a stronger lambda equals 0, like if this is less than 1 over log to the 10, then I'm losing a factor of log to cancel this log d, and I still have that this whole thing is less than 1 over log to the 9. But this is very strong now. It's because if you think about this convolution is always non-negative. One convolved chi of n is always larger than or equal to 0. And in particular, those primes p for which chi of p is 1, when you look at the convolution, it's what you get is 2. Because you get a 1 from here and a chi of p from here, and you get 2. So this sum is like 2 over n. Now, if I look at the sum of 2 over n or the sum of 1 over n up to here, this will be asymptotic to like a log of d to the a minus a log of d squared. So this is still asymptotic to a constant times log d. But now we know that it's much smaller by the assumption of existence of lambda equals 0. So it means this forces automatically in a rigorous way that most of these primes are such that chi of p is negative 1. Now, if chi of p is negative 1, it means that at least for prime numbers, chi of n looks like the Möbius function. And since both of them are multiplicative, of course, this is completely multiplicative, but the Möbius function is not. But at least for square free integers, chi of n does look like the Möbius for most values of n. Okay, now for the second part of this talk, we're interested, talking about myself and my co-authors that I'll mention in a moment, Hung Bui and Kyle Pratt. We were interested to see how an assumption of the existence of a lambda equals 0. So we don't need like an infinite sequence of lambda equals 0. One bad enough lambda equals 0, see if it has an influence in a certain range on central values of L functions. The central values of L functions have been studied for a long time. We start with Dirichlet L functions, and so let's see what we do. We assume. So we will assume later, but first I have to cite some other results. So let's not assume anything. We look at Dirichlet L functions. We look at so this psi is a character modulo q, and it is believed that L1/2 chi, so that the Dirichlet L function is not 0 at the central point 1/2 for almost all psi mod q. In fact, it is believed that they are never 0. I don't think anybody found any Dirichlet character for which L1 psi is equal to 0. So that would be the strongest conjecture. Now, Balasubramanian and Murthy in 1992 showed that the positive proportion of L1 psi's, these are non-zero. Ivanets Sarnak, 1999, developed a stronger method and showed that at least one third of these Dirichlet L functions are non-zero. At the central point are non-zero, and this is unconditional result. Hung Bui in 2012 introduced some refinements and improved the percentage to 34.11. And Khan, Milicevic, Go in 2020, last year, improved this to 38.46, I think. But this is only when Q is prime. The previous results that I stated here are for general Q, and all these are unconditional. And on GRH, it's known that at least 50% of central values are non-zero. And one can, if one instead works with the derivative of these functions, then one can prove that higher and higher percentages of these derivatives are not zero at the central point. Bui and Milinovic in 2011 obtained a lower bound on the proportion of psi for which the k derivative is not zero, of the form 1 minus big O of 1 over k squared. Let me rephrase this. So what do we mean by this thing? So they take all Dirichlet L functions modulo q, fix a k, look at the k derivative, and let q go to infinity. This means we average over the characters. So then we look at the proportion, how many of them are non-zero. And then we get, as q goes to infinity, we get a certain, or they got a certain proportion. So that proportion is a number that depends on k. And if we now look at the numbers that they obtain, as q goes to infinity, and now we let k go to infinity afterwards, we see that it goes to 1. And they are like 1, they're larger than 1 minus some constant over k squared. So the proportion goes to 1 at k goes to infinity. And of course, we expect the proportion to be 1 because we expect none of them to vanish. And for the first derivative, for instance, they obtain 75% already of LF psi have at most a simple 0 at s equals 1/2. And this is roughly on par with what one obtains from GRH. So we ask ourselves, if we assume the existence of a Landau Siegel 0, what happens with this proportion when we take higher and higher derivatives? Does it, we already know that unconditionally it goes to 1. Does it go to 1 at a faster rate? There wouldn't be a satisfying result. The satisfying result from our point of view was if we find a k and give you, this is a k for which the proportion is already 100%. And this is what we did. And we found that k, for k equals 1, we already pushed it to 100%. So let's say the result from 2020, as I said, joint work with Hung Bui and Kyle Pratt. Now it fixed a number c larger than 300. And then we say for any epsilon larger than 0, forget about the epsilon, I'm going to take epsilon to be 1/4. It doesn't matter. It's not the epsilon from Siegel's theorem or anything. Epsilon is 1/4. Okay. And any prime number between d to the 300 and d to this number c that we chose, a fixed number strictly larger than 300. We count here all the characters. So starting primitive characters, okay? We count those for which the value is not, it's not 0. The central value is not 0, divide by the total number of characters. And we show that this is larger than or equal to 1/2. It's 50%, that's not 100%, not what I advertised. But this is for the function itself. What I advertised before was for the derivative. For the function itself, we get 50%, and an error term. Now the error term, I said it's the first part is good. It's 1/square root. I said take epsilon to be 1/4, so it's 1/4 root of q. We don't care. But the other part, however, has a large power of q in it. It's 25/2 plus 1/4. What do we do with this? We cannot do anything except assume that L1 chi is small. But if L1 chi is small is like less than 1/log to 100, that's good enough. More than kills this term. This then L1 chi to the 1/2 is less than 1/log to the 50, and it dominates this. Okay, so then we do get 50%.
Sorry.
In a certain range, and the range is between d to the 300 and d to a fixed number c. Yes, please.
L chi's conductor q also?
Yes. Okay. Psi, no, sorry, no.
When we assume L1 chi on the.
Oh, yeah. This was chi d. Yeah. And then I dropped the, so then I don't type like the too much.
Oh, chi is got
chi all the time.
Sorry, that's capital
D.
Okay.
So this is modulo d. But the average or the proportion,
and q is going a very large power of d. Okay,
very large power of d. Yes. So this can match what's known under GRH. And the second result is that when k is 1 already, the proportion is 1. So in other words, if you have like 100%, have at most a simple 0. So multiple zeros, if we count multiple zeros, there will be 0%. So more precisely, assume the same hypothesis as in the previous result. Then the number of characters mod q, actually not the number, because the number will be q times this, or phi of q, the Euler function times this, is the proportion of psi mod q. something wrong here. It's not the number, but this word should be replaced by the proportion of characters psi mod q, such that ls psi has a multiple 0 at 1/2 is less than something that goes to 0 as q respectively d go to infinity. So it's less than 1 over square root. It's exactly the same thing, same expression, meaning that almost all have at most a simple 0. And now the last, the last part of the talk. Now we look at a more subtle problem. Don't ask me why it's, there's no time to say why this is more subtle, but you can ask Peter why. So we look at new
More
forms.
subtle?
It's much more subtle because of a result that I'll mention that he and Henrik proved. Okay. That if you are not careful and you obtain a result that's too good, go past 50%, then they disprove the existence of Landau Siegel zeros. So then it's we're talking about much more difficult type of results here already. So anyway, we'll look at F's in S2, Q. So we're talking about new forms, a way to prime level Q. And first of all, these L functions are self-dual. The root number is plus minus 1, but it's not always plus 1. And if the root number in the functional equation is minus 1, then the L function will have to vanish at the central point automatically by the functional equation. So there's nothing we can do about it. You cannot push it to 100%. And about half and half unconditionally are known to be odd or even. We say that F, just terminology here, F is even, or LFS is even if the sign is plus 1, and it's odd if it's minus 1. And we also denote by R sub F for each F the so-called analytic rank of F. So the order of vanishing of the L function at the central point. Now we knew already from work by Kowalski, Michel, van der Kamp, already 2000, that unconditionally they show that the proportion of F's with analytic rank less than or equal to K goes to 1 as K goes to infinity. And I think, yeah, I wanted to, there's no time to see, let me just read from their abstract, saying, because they did more than just what I'm saying. They look at primitive forms of way 2 and prime level Q, and this is also our context where we will look, and they fix a K. So the weight is 2, that they fix a K, and they look at the proportion of primitive forms such that this is the completed function. So they look at the L function, and then you multiply by the gamma function there, gamma factors, and Q to the S over 2 and stuff like that, and you get a completed function. And then you look at the derivative of the completed function. But this is a function that's already real on that line, and the order and the functional equation shows that the function is odd or even. The function itself is odd or even with respect to the central point. So either the order is odd or the order is even, and it's about half the time. So if you look at just the values, about half of them already are the values are 0, namely the odd ones. If you look at the first derivative, then the even ones, automatically the first derivative will be 0. So half of them will be 0. So that's why the best possible result is 1/2. That's why I'm saying in this terminology. But if you look at what this means in terms of the analytic rank, of course, the two functions have the same analytic rank because the gamma function doesn't have any zeros. So the L function and the completed function have the same order of vanishing. All right, so the proportion goes to 1 unconditionally. So what we show, before what we show, let's see what's conjecture. Brummer 95 and Morty still 95 they conjecture the best possible result here, meaning that if you look at the even f's, almost all even f's are, the L function doesn't vanish. So the analytic rank is 0. And almost all the odd ones have analytic rank 1. So they are forced to vanish at the central point because of the functional equation, but then the conjecture said they don't vanish anymore. The first derivative is already not 0. So that's the expectation. But they cannot make it like in the case of Dirichlet functions, the conjecture that every single one doesn't vanish. Like for Dirichlet function, we don't expect any Dirichlet function to vanish at the central point. But here, of course, we do have, because we have, say, L function associated to elliptic curves that have a high rank, and then, by Birch and Smelton-Dyer conjecture, they will also have high order of vanishing there. So, but almost all should not, and that's their conjecture. So we expect 50. So in conclusion, we expect 50% of the forms to have analytic rank 0, and we expect 50% to have analytic rank 1, and 0% of forms to have analytic rank 2 or more. Now, Henrik and Peter in 2000 show a lot more than what I'm saying here, that this conjecture basically implies there are no lambda Siegel zeros. Let me actually have a look at their paper now, if I have a minute. All right. And no time to go over more of the paper, but they look at 2 different families. You may remember that in that paper, they look at 2 different families. And one of them is this one. So when you fix K, the weight, for instance, weight is 2 in our scenario, or Kowalski-Michel van der Kamp scenario. And if chi d of minus n is 1, then what this notation means in their paper is an average. You take an average. Actually, it's an operator. They define that you take the sum where you take over all f's with this property. So they work. I mean, you take all of those that are even, then separate all of those that are odd. But those that are odd already, you know that are 0. And then if you divide by n, then you get a number like a proportion. But they don't divide by n, not yet. So the sum actually is asymptotic to n. What is this n in our previous notation is little q, and for us is the prime. But they don't even need this capital N to be a prime. This capital N is square free. We will work with, but such that the Euler function is asymptotic. In particular, when n is a prime, and they do show that out of this average of this type of L functions that have nothing to do apparently with Dirichlet L functions, because what this means is they take an f and they look at the value at the central point, and they also take f and they twist by chi. They look at the same L function, but they twist by chi, or our chi d. And again, look at, but that's not our Dirichlet function. That's what I want to point out here. It's another f of the same, it's another GL2 object. So there is no Dirichlet function. So that, here, so this is very interesting. You take an average like that, and they are able to recover from this average the value of GL1, or in other words, the average of the value of Dirichlet function, not at 1/2, but at 1. So that's a clear attack on Landau Siegel zeros. I don't know if this was confidential or not, but I remember Peter told me at the time, okay, it looks like maybe we got it, because and we ordered a bottle of champagne. Do you remember you telling me this thing?
I'll tell you afterwards. Finish your lecture.
Yeah, okay. This is what was done. But in fact, they optimized it and they went with 50%. And just to finish, I see I'm going over time here. I just wanted to, sorry. I'm sharing this screen again. I just wanted to look at our result. Let me go here just to state the result. In simple form, assuming Landau Siegel zeros exist, in some range, 100% of forms have analytic rank less than or equal to 1. Well, again, if chi of q is 1, and 100% of forms have analytic rank less than or equal to 2 if chi of q is -1. But if we put both of them together, it means that 100% of forms have analytic rank less than or equal to 2, which means 0% of them have analytic rank larger than or equal to 3. Now, this says nothing new about those that appear in, unfortunately, those that appear in Henrik and Peter's paper. But for those that do vanish at the central point, the odd ones, it does give us satisfying answer. It shows that 100% of them are vanishing of order 1 exactly. Because if they don't vanish, if they vanish at higher order than 1, that because they are odd, they will vanish at order 3 at least. But we show under this is not conditional. This is not unconditional. This is conditional. We show under the existence of lambda Siegel 0 that in fact 0% have order larger than or equal to, have order of vanishing larger than or equal to 3. And the last thing I'm going to just put on the screen is the actual state, not this. Let me close this. The actual, which is...
So wait a minute. You prove the conjecture of Brummer then under this assumption?
Under this assumption, yes.
Yeah,
yes.
okay. But you prove that the rank...
But only for odd ones. That almost
okay,
all
but
odd
you're
ones.
proving... So you're actually proving that the rank of J naught n, I think enough is known towards Birch-Schwinnet and Dyer that you can go from analytic rank to Mordell-Weil rank.
Yeah.
So you're proving that the rank of J naught n is asymptotic to n over 2.
Right. Okay.
Assuming
stated somewhere else. I think that's.
In other words,
that's the wrong paper. There's the Dirichlet function.
Okay.
This is it where we have. Yeah. This is the one where I was worried. This is one way of stating exactly as as Peter mentioned, that the rank is asymptotic because I have a log over log, but in a certain range and under strong enough. I mean, but not too strong compared to Siegel's theorem. It's not like 1 over d to the epsilon. It's 1 over log to a power of d. Henry will sympathize with us, and because he and Friedlander in some of their results, they need 1 over log d to the power 20,000. I mean, you see what that I mentioned before. But this is, it depends on this is what's come from the computation of this. But this says yeah. But in the other case, you see, we don't have any asymptotic. We are off by a factor of 2 here for lower bound and upper bound. And again, it's the same problem that Peter faced. So I'll stop here. And apologize for going over time.
All right, let's all unmute and clap and thank Alexandru for a great talk.
So if I understand, the result is very much in, I guess, in the flavor of Heath Brown. You assume that you have, as you're pointing out, you have a certain range. So if you want an infinite statement, you'd have an infinite sequence. But the existence of a Landau Siegel 0 allows you to say something quite dramatic.
Yeah, in a finite range, but in that range we don't even need we don't even need to average over Q. This holds true for every single Q separately.
Fantastic. Yeah, that's And what's interesting, yeah, unlike the Heath-Brown case, in the Heath-Brown case, you assume there's a Landau Siegel 0, and then you deduce the infinitely many twin primes, but there's no assumption of assume Riemann, assume anything you want that gives twin primes. So there's no complement to go with that. While here, the half and the 1, so we just needed to go to 51%. Somehow one feels much closer to having ineffective proof, in the sense that you would prove the thing unconditionally, but without knowing which route you took. So yeah, it's a great thing. Yeah, very interesting. I like it. And
your work with Henry was main motivation behind our work. And we said, well, this looks too technical to try this first. Let's try the Dirichlet function first. And that took a year. And
yeah,
then
well,
we said, okay, now
we went the same way. We went the same route. I mean, yeah, I want to let other people ask a question. Then at the end, I'll tell you the story. Yeah.
Okay, yeah. The story about how you got 50%, and I have thought a little initially that you might be able to get to do something strictly larger before you optimize.
Yeah.
I think literally what you told me is that, okay, we got 50% and we didn't even optimize.
Yes, right. That's correct. We got 50%.
We're going to optimize it tomorrow.
Yeah, and then we'll get 51% and we'll win. But then out of the ashes came a Dirichlet character with small conductor, which killed all our good work. It was like, yeah, we did celebrate too soon.
So I was right to remember that you did mention that you.
Yeah. We thought we had it. We thought we had it. God punished us.